Hello, Year 12. Today we're talking about motion under gravity and how to use Suvat when you've got an object that has acceleration on it that's caused by gravity. Okay, so how does gravity work then? Well, we know it's a force that causes attraction between two objects, and the greater the sizes of these objects, the greater the force of gravity that's acting on them. But more specifically, we're going to talk about how gravity causes acceleration. So we've got to pretend that these are two objects that are falling towards the Earth. And we're going to model it as if there's no other external forces other than gravity. There's no parachute, there's no air resistance or drag or buoyancy. And what happens is, on Earth, the acceleration that's caused by gravity is constant. So although these objects have different mass, the acceleration towards the Earth is going to be the same. And because this acceleration is constant, we give it a name, and the name for that number is g. And if you do physics, you'll know that this is about 9.8 meters per second squared. Okay, I think in physics you're told to use 9.81 sometimes, but make sure for mechanics you're using that number exactly, 9.8. Okay, so 200 kilograms for my baby elephant, that's the acceleration towards the Earth. For the toilet roll, it's got a smaller mass, but the acceleration is still the same. It's still this value of g. And again, we're not pretending that there's any air resistance or anything like that. It's just falling as if it's in a vacuum. So A equals this value of g again. Okay, if I were to put these objects on the moon, then the moon is smaller. The masses are going to be equal because the sizes of the objects, the amount of matter that we've got hasn't changed. But the acceleration towards the moon is going to be smaller than it is on the Earth because the gravitational strength is weaker. So for the moon, I believe the acceleration on the moon is only about 1.62 meters per second. Okay, so when we're talking about objects that are falling or acted on by gravity on Earth, we're going to be using this value g here, 9.8 meters per second squared. Okay. If you want the weight of an object, as opposed to the mass, because they're different, the weight is calculated by Newton's second law. So the weight is a force. It's the force pulling you down towards Earth is your weight. The force is given by mass times acceleration. Okay, so if you know those two things, mass has got to be in kilograms, acceleration under gravity is going to be g, then you can work out your weight. For the elephant, should we do that one? So the weight of the elephant is (200 times g), and g being 9.8, we get about 1960. And then the force is going to be in newtons. Okay, so make sure you can distinguish between the mass and weight, which incorporates the acceleration of it as well. Okay, all right, so if I give you another picture, here's a picture of some books that are resting on a shelf. You might be asked to label up on the diagram all of the forces acting on the object that you've got. Okay, and we're going to pretend that all of these books are just one big object kind of stuck together. Okay, so what we need is, if we put the mass on our books, let's put a mass on, I don't know, let's make it 3 kilograms. Okay, that's the amount of mass for the books. Then gravity is going to cause a downward force towards the Earth. And that's going to be given by mass times acceleration, which is 3 times g. Okay, so objects on this picture, there's going to be a g that represents the weight, or at least part of the weight force. Okay, now because we've got this force acting down towards the Earth, the books also aren't falling through the desk, they're being held up by the desk. So in addition to this force that's acting downwards, there's this opposing force as well, acting against this motion and perpendicular to the shelf, that we call the normal reaction force. Okay, so this is a force that if any object's resting on something, if it's resting on a shelf or on a sheet or on something like that, then there's this force that acts perpendicular to what it's resting on. And it also depends on any acceleration in that direction. Now, my books are staying still. There's no acceleration being caused because they're just resting on the shelf. So this is going to equal the downward force. Okay, if we do something else to our books, if we want it to slide along the desk, if we want to drag it this way, then there might be a force acting this way that's pulling the books along. And we may wish to add friction back the other way that opposes the motion. If we've got a rough desk, then friction will act back this way. And that's all we need to label up all of our diagrams. Okay, but the important bit is that you've got weight, that's mass times acceleration, and then if it's resting on the shelf, then you've got this normal reaction force as well. Okay, keeping it upright, not letting it fall through. Okay, right, some practical examples then. We're going to use Suvat and we're going to incorporate gravity to do some calculations that use Suvat to figure out things like times and heights and things like that. So you've got to imagine this is a football that's been kind of that's dropped out of the gutter and it's about to fall onto the floor. Its initial height is 8 meters, and I want to know the time it's going to take to hit the floor. Okay, and obviously the ball's being acted on under gravity. We're removing anything like air resistance. We're just modelling this ball as a particle and seeing how long it takes to hit the floor. Okay, so this is a Suvat question. I'm going to write Suvat down like we've done with our other examples. Okay, and then before we put values in, whenever you do a question, it's always important to choose your direction that you're resolving in, okay? Which direction are we going to choose to be the positive direction, okay? And because the motion of the ball is going to be downwards, I think it makes sense to resolve in a downward direction. Okay, so anything that acts downwards, we're going to take to be positive, and then anything that's going to be acting upwards will then therefore be negative. Okay, so we're hitting the floor from where we started up here. The displacement we're going to have is going to be 8 meters, and that will be positive because we are having displacement downwards towards the floor. Our initial velocity, well, we've started off with our ball at rest, okay? There's no downward velocity when we initially start to fall off of the gutter. So my initial velocity is going to be 0. I'm going to put at rest. Okay, the velocity when we hit the floor isn't really needed for this question, so I'm going to leave that bit alone. I'm not going to use it. But my acceleration, well, in the downward direction, my acceleration is going to be g due to gravity. Okay, we're not doing this on Mars, we're doing this on Earth, so it's going to be 9.8. Okay, and then time, that's the thing that I want. So I'm going to put it as a question mark, that's the thing I want to work out. And then with this information, we're going to work out which of our Suvat equations is the best to use. Okay, and I reckon that the one that uses U, S, A, and T is going to be this one. U, T, of the 5, this is the one that uses those 4. T squared. Okay, so that's what all of these numbers are going to go into. Let's put the numbers in. Double check that you've got everything without any missing minus signs in. Okay, everything's pointing downwards, so no minus signs. S is 8. U is 0, so this term over here is going to be 0. Okay, then A is 9.8. I'm going to put that where the A goes. And then we've got T squared, which is our unknown. Okay, then it's just a matter of solving for T. So I'm going to tidy up. Half of 9.8 is 4.9. I'm going to divide by 4.9. I'm going to do that in a second. That gives me about 1.63, which is t squared. It's roughly 1.633. Take square roots. Now, we obviously don't want a negative time. We can ignore the negative version of that. So just positive square root's what we need. And that gives me roughly 1.2 8 seconds. Okay, so that's using Suvat, and using our motion under gravity, acceleration is 9.8. Okay, I'm going to do one more example, and I'll leave it to you to do some yourself. Okay, so here's my second example. Somebody's throwing a ball. They're throwing it up vertically, but they're starting off their throw with a height of 2 meters. And we are projecting it upwards with an initial velocity of 20 meters per second. Okay, so I'm going to add that to the picture because it's not there already. Remember, we use single arrows for velocity, so that goes there. That's going to be 20 meters per second. Okay, and it wants the maximum height attained by the ball. All right, so we're looking for how high we are up here once we've got to the top there. I'm going to put that vertically. Okay, so if I can work out that height, I can then add 2 meters, and that's the maximum height attained by the ball off of the ground. So let's write Suvat down. So we'll get us started. Okay, and again, we need to choose a positive direction to resolve in. And I think it makes sense this time because we're throwing upwards. It makes sense to resolve upwards. That's our positive direction. Okay, S is the thing that we want. And bear in mind, we're starting off our Suvat at 2 meters up from the ground. We're not taking the 2 meters into account. We're just putting S for how high up we are. We're going up here. Our initial velocity, that's 20. That's given over there. Okay, now at the top of our parabola that we've got when we throw our ball, once we've got to the very top, the velocity is actually 0. Okay, we've started off by traveling upwards. We've got to the middle of our journey at the top, and we're actually horizontal. Okay, and if we're horizontal at the top of our peak, then there's no upward velocity. Okay, that's where the ball turns around. It's got positive velocity on the first bit, 0 at the top, and then negative velocity on its way down. So my V is actually going to be 0. Okay, and then for A, remember we're resolving vertically, and gravity acts towards the Earth. So for this one, A is going to be minus 9.8, minus G. Okay, just compare that to what you've got over here. And then time, we don't really need time. It's just the height that gets to the top, and we've got 4 values, so we can get started. Okay, and the Suvat equation for these 4, if you check your 5, the best one to use is this one. That's a squared. V squared equals U squared plus 2AS. Put the values in. V is 0. U is 20. If I square 20, I get 400. And then I've got, I'll have minus, because of the minus that's over here, minus 2 times 9.8 times S. Okay, I'm going to solve for S. I'm going to add the term over here to the other side and divide, so that's 400 over, and then 2 times 9.8 is 19.6. Okay, so I'm going to divide those. 400 divided by 19.6. That gets me 20.4 meters roughly. Okay, that's the height that's obtained from where you started at the top of the hand. If I add the 2 meters onto that, I'm going to get the height from the ground. So my answer is 22.4 meters. Okay, that's part A done. The time taken to hit the ground, I can do that as well. But what I'm going to do, I'm going to start from the beginning of my journey again, from the beginning of when I first launched the ball. So I'm still going to resolve upwards, just to maintain a bit of consistency. But from where we started, I'm trying to get down to the ground that's 2 meters below where I started. So my S value this time, resolving upwards, I'm going to have a displacement of -2 meters. Okay, that's from where I launched the ball. Everything else can go on if I need to. Okay, U is my initial velocity, 20. And it's positive because we're launching upwards and we're resolving upwards. V, well, the velocity at the ground, don't really care about that. I'm going to leave that alone. A is minus 9.8 again. And T is the thing we want this time. Okay, so using those values, you can think about which equation is the best one. It's going to be this one again. Quite a common one to use, this equation. It happens quite a lot. ut plus a half at squared. Sub your values in. So minus 2 equals, okay, 20t. Half of A is half of this value here. I'm going to do minus 4.9 t squared. And that produces a quadratic equation in t, which we can then solve. Okay, so I'm going to put everything onto the positive side, make a quadratic equation. 4.9 t squared, it'll be minus 20t, and then minus 2, and that equals 0. Okay, now to save a bit of time, I'm not going to show the method that I'm going to use, but what in an exam I do want you to write down the way that you're going to solve this equation, which is going to be normally by writing in the values in your quadratic formula. So I'm just going to put formula, but you're going to write down what values have gone in. Okay, so then t equals, give me a second, I can type that in. So using the formula, 20 plus, first roots is this. Okay, so I make the first root as being 4.18 seconds. Okay, and presumably if I have the negative version of this answer, I'm going to get a minus value of t, which I don't want. But let's just double check that. If I do 20 minus square root, fill the rest in. Yeah, okay, so 4.18 is the first answer. The second one is minus 0.10, roughly. Okay, clearly this is not the right answer because that's a negative time, so it's going to be this one. That's in seconds as well. Okay, so that's how to use Suvat with gravity. Okay, best of luck. If you've got any questions, you can give me an email or send me a comment on Show My Homework, but hopefully you've got not much trouble with those questions. Okay, thanks guys.